consider the solar system.
Over the last 4 centuries, this is how we've come to see it. 8 planets revolving continuously in elliptical orbits around the Sun, each following a precise mathematical path defined by the laws of celestial mechanics. But our understanding of the system did not emerge fully formed. It evolved over centuries of observation, debate, and technical advancement. In fact, up until the 1500s, we didn't see the solar system like this at all. We saw it like this. The Earth fixed at the center, and all the planets revolving around it in a complicated dance. Without elliptical orbits, things were much more difficult to describe. Let's fade out the other planets, and the Sun, and just look at the orbit of Mars. For millennia, this is how it seemed to move, revolving around the Earth, but occasionally turning back on itself to create a looping pattern known as a spirograph. Try to remember the shape of this curve, as later in the video, we're going to try to use math to reproduce it. For now, let's bring the rest of the planets back in and zoom out. Without the ellipses, it's not hard to see why ancient astronomers thought that the Earth was at the center. Doesn't it just seem obvious? From this perspective, it's almost impossible to see how you could put the Sun at the center. And yet, when you bring the ellipses back in, it's almost impossible to see how you could not. Over the years, we came to accept that it is both more accurate and more elegant to put the Sun at the center instead of the Earth, and this model, called the heliocentric model, is still what we use today.
It's hard to overstate how significant this paradigm shift was. I mean, to put it into perspective, before Copernicus, Earth wasn't even considered to be a planet. It was simply the world, an unmoving anchor for the whole universe. The planetae, or wanderers in ancient Greek, were things that seemed to move against the backdrop of the fixed stars. Earth didn't move, so it didn't count as a planet. To the ancients, only 7 things did: Mercury, Venus, Mars, Jupiter, Saturn, and the Sun and the Moon. All of them seemed to wander across the sky, and so all of them counted as planets. Earth itself sat at the center, motionless, excluded from the celestial family entirely. It was a different category of thing, corruptible, dense, messy, a sort of cosmic basement level, whereas the stars and the planets belonged to the ether, a purer celestial substance. Everything heavy was dragged down to the earth, while heaven danced above us, light and free, perfection, order, beauty. It was a dwelling place fit for the gods. But then, in 1543, Polish astronomer Nicolaus Copernicus published a book that would change everything. In his De Revolutionibus, Copernicus introduced a model that placed the Sun, not the Earth, at the center of the solar system. Today, his perspective seems obvious, even trivial. But in the 1500s, it sparked more than a century of fierce debate and research. Copernicus had done more than just shuffle the order of the solar system. He had unseated humanity from the center of the universe itself. The whole cosmic caste system collapsed, and we came to see ourselves not as living in the world, but on one world, orbiting one star in one galaxy among countless trillions of others. It's weird to feel how deeply the concept of planet shifted underneath our feet. What seems today like an obvious natural category was once just a nickname for a handful of bright sky wanderers that you could track with the naked eye. What would it be like to go back to that? To once again see ourselves as the center of the universe? Well, here's an interesting fact that not too many people know. When Copernicus first introduced his model, it was not actually better at predicting the motion of the planets than the best geocentric models of his day. In fact, nearly 200 years before Copernicus introduced his theory, a Muslim astronomer named Ibn al-Shāṭir designed his own model of the solar system which, for several bodies, made mathematically equivalent predictions to what Copernicus would later propose. The only difference? Ibn al-Shāṭir kept the Earth at the center. 2 different scientists landed on the same mathematics through different worldviews. Isn't that crazy? Ibn al-Shāṭir's theory was just as predictive as Copernicus's theory, despite keeping the Earth at the center. It got me thinking, could we design a more modern geocentric model? Could we design a model that was just as accurate as, say, Kepler's model, but keep the Earth at the center? Well, the answer is yes, and in this video I'm going to show you exactly how to do that, and I'm also going to give you an idea of how humanity might have come to invent that model instead of the model we have today in a world where Kepler and Copernicus never existed. But before we get there, let's take a look at how astronomers modeled the cosmos in the centuries before Copernicus was born.
This is the Ptolemaic model of the solar system. It was invented by the Greek astronomer Claudius Ptolemy in the 2nd century to explain retrograde motion, the way that planets like Mars sometimes appear to stop, move backwards a little bit, and then turn around and continue in the direction they were moving before. To do this, he theorized that planets follow epicycles, small circles that orbit around a bigger circle called the deferent, which had the Earth at the center. Not only did these epicycles allow him to explain why planets sometimes seem to move backwards, they did it using perfect circles, which really mattered to ancient philosophers because they believed circular motion was more perfect and divine than other kinds of motion.
So, for well over 1,000 years, Ptolemy's model was the cosmos, Earth at the center, planets riding around on nested circles, and astronomers tweaking the size and speeds of those circles to better fit the data. Here's a drawing of the orbit of Mars made by Giuseppe Bianconi that follows a Ptolemaic model. Notice how it has the same spirograph shape we saw earlier? From the point of view of an observer on Earth, the path that you get out of Copernicus's model can match what you get out of Ptolemy's epicycles to essentially the same accuracy, at least with the precision of pre-telescopic measurements. But even though Copernicus rivaled Ptolemy, his model wasn't yet the most accurate. That breakthrough wouldn't happen until 1609 when Johannes Kepler proposed his elliptical model of the solar system. And it's that model which we are going to transform from heliocentric to geocentric in this video. Now we're about to dive into some pretty advanced mathematics, so if that isn't your thing, feel free to jump ahead to this timestamp and continue watching the video from there. The reason I'm including the math is to convince you that the geocentric model I'm about to propose is not only accurate, but computationally identical to Kepler's model. If you find this section tough to follow, I recommend an excellent video by Burkhard Polster on his YouTube channel Mythologer, link in the description below. With that out of the way, let's take a look at how we can take Kepler's model and transform it into a geocentric model that actually works.
Kepler's key insight was that orbits are not circles but slightly distorted circles called ellipses. He also theorized that the Sun wasn't at the center of the ellipse, but one of its two focus points. Ellipses make things a bit harder. If we had a circle, every point would be the same distance from the center, and if you swept an angle around, the radius would never change. If you stretch that circle into an ellipse, things stop being so friendly. Suddenly, the distance from the Sun changes with the angle. That means the simple trick we use with circular motion, just measure an angle and you know where the object is, doesn't work anymore. Two different angles can give completely different distances, and the geometry no longer lines up cleanly. And it gets harder. Planets don't even travel at a constant speed. They move faster at perihelion, when they are nearest to the Sun, and slower at aphelion, when they are furthest from the Sun. So Kepler's job was to take a lopsided elliptical orbit that speeds up and slows down and convert it into something perfectly uniform, a steadily increasing angle. Let's call this uniform angle m, which is short for mean anomaly. M behaves super simply. It just increases at a steady rate like a clock. In fact, we can even call it our uniform clock, as it is just the angle a perfect clock hand would have if the planet moved in a circle with constant speed. The rate it ticks at is set by a constant called n, the planet's mean motion. You can think of n as the planet's average angular speed. Different planets will have different values, but the concept is the same. m0 is just the angle that we're starting from, and t0 is our epoch, which just means the time that we are starting from. For our calculation today, we'll use January 1st, 2000 as our epoch. In Julian days, this date can be represented as a number. This is a standard epoch in astronomy known as J2000. Now let's watch our uniform clock, the mean anomaly, move. Notice how it moves uniformly while the elliptical orbit speeds up and slows down? That's exactly what we want to have. We're going to need an equation that makes it possible to go between our uniform clock and the non-uniform eccentric motion of our elliptical orbit. To do this, Kepler introduced a second angle, E, called the eccentric anomaly. The eccentric anomaly is essentially the angle from the center of this yellow circle, called the auxiliary circle, which has the same width as the ellipse. You can get E by locating Mars on the ellipse and then moving vertically from it until you intersect the circle. It's a little tricky to get the hang of, so let's see how these angles talk to each other. Johannes Kepler showed that you can use the eccentric anomaly E to compute the mean anomaly m, our uniform clock. To do this, he devised this equation, called Kepler's equation. m equals e minus little e times sine of e. Little e is just the eccentricity, which is a measure of how stretched the ellipse is. If you go the other way around and use m to compute e, then you get a clean transformation from uniform circular motion to the kind of elliptical motion that planets exhibit, speeding up and slowing down depending on their distance from the sun. Let's hit play and see how it looks in action. And voila! Just like that, we have a geometric model that takes the steady clock on the right and turns it into the orbital motion on the left. And Kepler figured out all of this in the 17th century. Now, I know what some of you are thinking. Isn't this kind of convoluted? Well, the answer is yes. By modern standards, this is a contrived way to model orbital mechanics. But keep in mind that Kepler derived this system before Isaac Newton had formulated his laws of gravity, so the only tool he really had to work with was geometry. And as far as that goes, this model was a very accurate description of planetary motion. In fact, it was the most accurate model that had ever been devised. Isaac Newton himself would later prove that you can use his own laws of motion to produce these very same ellipses. So now that we have a reasonably accurate heliocentric model, let's go ahead and see how we might make it into something Earth-centered. We'll do it in 3 steps. Step 1 will be to get the equations of motion for Earth and Mars. After that, we will do a Fourier decomposition to transform the paths into epicycles. And finally, we will subtract the position of Earth from the position of Mars to make the whole model geocentric. In the interest of time, we're going to go through these steps quite quickly, but feel free to pause at any point to get a better idea of what's going on. And if you find yourself struggling to follow along, don't worry too much. It's university-level mathematics, and you won't need it to understand the rest of the video. Just sit back and enjoy the ride. Let's begin with step 1. This is the actual orbit of Mars. It's much closer to a circle than the exaggerated ellipse that I used earlier, but it's still somewhat eccentric. At any point in time, the x and y coordinates of Mars with respect to the Sun are given by these 2 equations. I won't get into exactly where they come from, so just take it for granted that they are a common way to parameterize an ellipse. There's just one adjustment that we need to make. Mars's orbit is actually slightly tilted, which means that we need to rotate it by an angle called the longitude of perihelion. If we apply the rotation to these equations, they get much longer and uglier. But the concept is just as simple. They just represent an ellipse that has been rotated slightly. Now let's introduce Earth's orbit. The equations are basically the same, just with different parameters. The equations can be condensed into a complex number, with a real part representing the x-coordinate and an imaginary part representing the y-coordinate. This just makes them a little bit easier to look at, and it will help us do the next step, transforming the ellipses into epicycles. Now, it's a bit outside the scope of this video to explain what a Fourier series is or how it works, but Grant Sanderson has some excellent videos explaining the concept on his YouTube channel, 3 Blue 1 Brown, which I will link in the description below. For now, if you don't understand what's happening, don't worry. All I'm doing is transforming the elliptical orbits you saw earlier into a series of circles called epicycles. It will hopefully make sense in a minute or two. For each planet, we take its Fourier expansion with respect to the mean anomaly m, and then compute the complex coefficients with a discrete Fourier transform. Now, we can make a few simplifications. First, we can plug the mean anomaly into the equation. Next, we can substitute this long expression here for a simple coefficient, capital C. Finally, we switch out k times n for a frequency term called omega. And that's it. Now we have an epicycle series for Mars, and an epicycle series for Earth. Let's take a look at how it works, term by term. Each term in the sum represents an epicycle. This constant, c, represents the radius of the epicycle. This constant, omega, represents the frequency at which the epicycle rotates. Let's add another one. This yellow epicycle has a different c and a different omega. It is smaller and it rotates at a faster speed. Let's see how that looks. It's a little bit more complicated, isn't it? Let's add a few more and watch the whole system go. Now the motion is very complicated, and we can tune all of the parameters to make these epicycles trace out any shape that we want them to, including the orbit of Mars. The compact way of expressing all these epicycles is just that sum we saw earlier, this one, which we got from the Fourier transform. Now we can do step 3, subtracting Earth's epicycles from the Martian epicycles in order to make the whole thing geocentric. This is the simplest step by far. You just take the Fourier series for Earth and subtract it from the Fourier series for Mars. The result is a single combined sum, which we can represent as a table or list of epicycles. These are the actual calculated values for our epicycles. The j's in the equation are just a way of numbering the rows of the table. And, just like before, each epicycle has a radius c, a frequency omega, and an initial phase offset, which is included in c. We didn't explicitly show this earlier, but it has technically been there the whole time. Taken together, this table makes a list of epicycles that, when added together, will trace out the path of Mars with respect to the Earth. Because we subtracted Earth's epicycles from Mars, there are entries from both planets. The red ones come from Mars, and the blue ones come from Earth. I've kept the table to 6 rows to keep it simple, but you can actually add as many epicycles as you want. The more you add, the more accurate the model will be. Lastly, this top term is a non-rotating line that we can call our DC offset. It just represents the distance between Earth and the center of our largest epicycle. Technically, even in our geocentric model, Earth isn't quite at the center. It's a little distance away. Now that was a lot of math, so let's see how the model actually looks in action. This is our geocentric model for Mars. It's initialized to January 1st, 2000, the date we called J2000 earlier. The blue dot is Earth. It is sitting a little ways away from the exact center due to our DC offset. Let's see how the model looks in motion. Immediately, we can see it start to trace out the spirograph shape that we saw at the beginning of the video, which suggests that it's working. It may look like there's only 2 epicycles, but if we zoom in, we can see that the higher order epicycles are just really small. I didn't draw a dot to represent Mars because doing so would make the smaller epicycles hard to see. And, just like that, we have developed a geocentric model using Ptolemaic epicycles that is just as accurate as Kepler's elliptic model.
If you skip the math section, or are just feeling a little bit lost, here's the short version of what we just did. We started with Kepler's heliocentric model of Mars, an ellipse with the sun at one focus. We treated that motion as a signal and did a Fourier decomposition on it, breaking it down into a sum of circular motions, harmonics, each with a size and speed. If you draw those harmonics as literal circles on circles, you get a stack of epicycles around the Earth. The tip of the last epicycle traces out exactly the orbit of Mars, to the accuracy of Kepler's own theory. So in this sense, my geocentric epicycle model for Mars's position in the sky is computationally identical to Kepler's heliocentric model. If you feed them the same initial data, they will give you the same prediction for where Mars appears. Now, a very fair question is, how accurate is this model really? Kepler's original model did not include inclination out of the ecliptic plane, it didn't include the slow precession of the longitude of perihelion, and it didn't include gravitational perturbations from other planets. My theory is directly based on Kepler's theory, so it actually inherits all those same problems. It describes idealized planar two-body motion. So in that sense, my model is just as accurate as Kepler's model, but it is not more accurate than Kepler's model, and it is not as accurate as the best existing heliocentric models today. But that said, if we wanted to correct for all those things, we could just add more epicycles. Now that may sound like a cheap trick, but it's not. Modern celestial mechanics actually does something very similar in spirit. When modern astronomers want to correct their models, they expand their equations in series and add correction terms with different frequencies. Those are, mathematically, just epicycles with a different name. So the basic message is that epicycles were never wrong as a technique, they were just wrapped in the wrong physical picture of the cosmos. In the title of this video, I suggested that I was going to un-debunk geocentrism. So did we actually do that? Well, not really. At least not in the way that the phrase usually implies. What we did show is that you can construct a model that is geocentric but equivalent to our best heliocentric models. What we have not shown is that the Earth is really special or truly at the center of anything, really. Once you start looking beyond simple planetary positions and consider things like stellar aberration and parallax, the phases of Venus, and the dynamics of gravity under general relativity, the picture that emerges is that there is no absolute unique center of the universe, and there is no reason to privilege the Earth. So I've not resurrected the old philosophical idea that the Earth is the center of all creation, but what I have done is show that given the same observational data, you can construct multiple mathematically equivalent descriptions of it. And that has some interesting implications. It leads to a bigger question. What exactly is a model in science? Well, in very practical terms, a model is just a structured way of taking measurable inputs and using them to predict measurable outputs. You give it a number that you can observe, like time, mass, initial position, and it gives you a number that you can check against reality, such as where Mars is going to appear in the sky. A model that's very good at doing this is said to have high predictive accuracy. But, and this is the key point, high predictive accuracy isn't the same thing as being true. My geocentric model has the same predictive accuracy as Kepler's model, but it's a worse description of what's actually going on physically. It adds unnecessary complexity, it hides the elegant simplicity of elliptical orbits behind a pile of epicycles. You would never choose it to describe the solar system to somebody. But it raises an uncomfortable question. If it's possible to build a geocentric model that fits the data just as well as Kepler's does, then that suggests that our current best theories might themselves be, in a way, epicyclic relative to some deeper description of nature. Today our top-level theory is probably quantum field theory, and quantum field theory works extremely well. It's helped us make sense of a myriad of bizarre phenomena, as well as build complex technologies like particle accelerators. In the predictive sense, it is a fantastic model. But history tells us that we should be careful equating model that works extremely well with the final truth of the matter. It may be that some of the structures we build into these theories, symmetries, fields, higher order corrections, might one day look to us like epicycles. Technically effective, but not the most natural way to describe what's going on. Tweaking a theory to fit more data by just adding more terms is exactly the same type of thing as just adding more epicycles. Whether those tweaks are revealing reality or just fixing the curve is something we can only find out in hindsight once a better theory comes along. Take dark matter, for example. It's the name of an invisible form of matter that we can't directly see. We think that it might exist because galaxies seem to spin faster than what we'd expect for their given visible mass, but we don't know. We add dark matter to keep our current laws of gravity working, instead of just changing those laws themselves. That might mean that dark matter is a yet undiscovered ingredient of the universe, or it might mean that we've just built the modern equivalent of epicycles to save a model that will one day be replaced. We don't know. Now there's a strong objection you might have to my whole construction. Hold on, you might say. Your model only exists because you reverse engineered it from Kepler. Nobody in a pre-Kepler world could have done that. And this is a fair criticism. The way I actually built my model did depend on having Kepler and modern mathematics available. But it's worth asking a counterfactual. If history had gone differently, could something like my model have come about without ever going through Kepler? I think the answer is yes, in principle, just as long as somebody like Joseph Fourier came along. Here's one way that I think the alternate history could have unfolded. First, astronomers collect highly accurate measurements of Mars's position over many years, expressed as its ecliptic longitude as a function of time. Next, a mathematician discovers Fourier's ideas, that any periodic signal can be decomposed into a sum of sine waves, or circles geometrically. Next, they apply this technique directly to the Mars data, without any heliocentric theory in mind. The result is a set of frequencies and amplitudes, essentially a spectrum of how much each circular motion contributes to Mars's apparent path. This type of frequency strength plot is called a periodogram. From that periodogram, they infer an epicycle model like Ptolemy's. Each frequency corresponds to an epicycle, each amplitude to its radius, and the phases tell you where to place them. At no point in this process do you need to imagine ellipses around the sun. You can be a committed geocentrist and still compute the Fourier series of planetary longitudes, fit epicycles, and make excellent predictions. So while I derived my model from Kepler, the mathematical machinery doesn't actually require him. A civilization that discovered Fourier analysis before heliocentrism could, in principle, have refined geocentric epicycles to a high degree of accuracy using pure data science. That doesn't make geocentrism true, but it does show that it could have remained viable for a lot longer than it historically did. And that brings me to the question that I want to leave you with. If it's possible to hold on to a worse worldview like geocentrism and still fit the data extremely accurately by making the model more elaborate and complex, then in what areas might we still be doing something like that today? Where might we be clinging to a picture of the world that works while missing a deeper structure behind it? The point of this video is not to claim that geocentrism was correct. It's to remind us that our best theories are still just models, tools for making observations and predictions. They may work extremely well, but science alone can't ever tell us whether we've reached the final story or just a very good approximation. My name is Ethan. This has been Odd Science. Thanks for watching.